let's have some more fun with equilibrium. Let's think about this situation. We place a mixture of 2 moles of H2, 1 mole of N2, and 2 moles of NH3 in a 1 liter container at 472 degrees. So if we think about our ice box again, we know we have 1 molar of N2, we have 2 molar of H2, and we have 2 molar of NH3. Now, here's the rub here. If I want to find out the equilibrium concentrations, I first have to know which direction the equilibrium is going in, or the reaction is going in to reach equilibrium. Because before, all those other problems on the last video, we had reactants at the beginning, but no products. We knew it had to be heading that way, to the right. But here, I don't know if I should say minus x minus 3x plus 2x, or conversely, maybe the reaction's going the other way, and I should say plus x plus 3x minus 2x before I get to equilibrium here. Which one's right? The answer is I don't know. The only way to know that is to calculate something called Q. Q is called the reaction quotient. Q is essentially K not at equilibrium. So if we think about that reaction I just had, Q, just like K, is NH3 squared over N2 times H2 cubed. Now we plug those initial values in here. Those values were 2 over 1 times, that's 2 again, that one's cubed. Get out your calculator, plug and chug, and you get 0.500. Now, the thing to do is to compare Q to K. K, for that reaction, we know to be 0.105. Q is 0.5. That means Q is greater than K. What does it mean to say Q is greater than K? Well, let's think about this again in terms of this. Remember, this is a fraction, and for the number to be bigger, that must mean the numerator is bigger than the denominator. So if Q is greater than K, that must mean I have more product now than I do at equilibrium. And if I have more product under the Q conditions, it must want to get rid of product to get back to equilibrium, which means a shift from the products to the reactants. So if I go back to this page, we have to go from NH3, we have to get rid of some of this NH3 and go back to reactants. So now I can answer this question here, is it's got to be this bottom one and heading back that way in order for this to work. Okay? Let's draw some conclusions. If Q equals K, and the system is already at equilibrium, no further shifting will happen. If Q is greater than K, then, as we've said, the concentration of products must be too large, and the shift has to be to the left. some of the products must get used up and some more reactants will be formed until the equation reaches equilibrium again. And lastly, if Q is less than K, then the concentration of products is too small and more products need to be formed. The shift will be to the right. Some of the reactants will get used up and make some more product. All of which leads us to Le Chatelier's principle. Le Chatelier's principle says that if something happens to disturb an equilibrium, the reaction will shift to undo the disturbance. Let's think about this in practicality. Here is our generic equation, A plus B is in equilibrium with C plus D. Let's say we added in some more A. More A gets added into the beaker. Now the reaction is going to shift this way to the right to undo this extra A. It's going to use up all that extra A so that I can get back to equilibrium. Ditto if I add more B. Right. If you think about adding C or D, let's say I add a product, I add some more C, well then the reaction is going to shift back this way. It's going to use up all that extra C and form more A and B. All of this to get back to equilibrium. Now let's think of Le Chatelier in terms of gases, because there's a couple things where you really have to think about this. Let's make this generic equation A plus B is in equilibrium with C plus D. Only this time I'm going to put some coefficients in there. I got 2 moles of A and 2 moles of B going to C plus D. Now let's say I increase the pressure on the reaction vessel, this is all in, by decreasing the volume. I'm decreasing the volume. Now obviously that's going to increase the pressure. And I have disturbed the equilibrium. So what's going to happen is, according to Le Chatelier, is it's going to react to undo this increase in pressure. Which means it's going to shift to the side which has less moles of gas. Now this guy has 4 moles of gas, this guy has 2 moles of gas. So in this case, decreasing the volume will shift it to the right because that's the side with less moles gas. If, on the other hand, I add in an inert gas, something like argon, okay, that actually doesn't change anything at all. Okay? Because none of the partial pressures get changed. The whole thing is changing. Nothing's changing in relation to anything else. Okay? So that's one of the trick questions that they'll tell you is they've increased the pressure by putting in an inert gas. An inert gas doesn't change anything. Now suppose we're talking about temperature. Temperature, remember, is the one thing that's going to change K. All these other changes, they don't do anything to change the value of K. But temperature will. But whether the temperature, increasing the temperature, shifts the reaction to the left or to the right depends on whether it's endothermic or exothermic. If it's an endothermic reaction, delta H is positive for endothermic. And if delta H is positive and it's endothermic, that means you can think of the heat or the delta H as being a reactant. So if I increase the temperature, that's the same as increasing a reactant, and the shift is going to be toward product. If, on the other hand, delta H is negative and it's exothermic, that means delta H is on the product side. And this is just like adding a product. the shift will be to the left to undo that extra heat that got added in.